My name is Mark Herman. I'm with Kimley-Horn in Richmond. I'm currently one of the VASite section reps to Southern District. So I will be moderating this session, which is using data to support decision-making. And we are going to start off by thanking our sponsor for this session, who is AirSage. So I have a quick video from AirSage that I will play for you all. So again, thanks to AirSage for sponsoring this session. Just a few housekeeping things before I turn it over to the presentations. If you all have any questions, feel free to enter them in either the chat or Q&A pod as the presentations are happening. Once the presentations have ended, I will pass those questions along to our presenters after each presentation and make sure that we can get those answered. To start, we're going to kick it off to Saiful Khan for his presentation, which is titled Assessing Operational Impacts from a Planned Detour in Birmingham, Alabama. Saiful is a civil engineer who specializes in transportation infrastructure and traffic management projects. He has more than 8 years of professional and research experience. He obtained his bachelor's in civil engineering from Bangladesh University of Engineering and Technology in 2008 and a master's from the University of Alabama at Birmingham in 2020. Saiful worked as a research assistant at the UAB Trend Lab under the supervision of Dr. Virginia Sisiopiku. And he also worked as an intern at the Regional Planning Commission of Greater Birmingham, where he was involved in traffic congestion management and data analytics, and served as an officer of the UAB ITE student chapter. After graduation from UAB, Saiful joined the Sustainable and Resilient System Analytics Research Group of the University of Virginia, where he is currently pursuing his PhD program in Industrial Systems Engineering. So with that, we'll turn it over to Saiful for his presentation.
Thank you, Mark, for introducing me. So, can you please show? Okay. So, good afternoon, everyone. At first, I would like to convey my sincere gratitude to the organizer of the Southern District IT Annual Conference. I am really thankful for providing me the opportunity to present our project in such a platform. The title of our project is Assessing Operational Impacts from a Planned Detour in Birmingham, Alabama. So my today's presentations will cover these topics. At first, I will talk about the background of the study. Then I will describe the methods that we follow to conduct the study. And finally, I will focus my discussion on the analysis and results. So background of the study: for ratifying smooth traffic movement, road infrastructure should have to be maintained regularly. And to carry out our repair and maintenance work, construction work zone often occupies the existing roadway, and sometimes it is necessary to close road segments fully or partially. So in either way, detour plan is essential during the road closure to provide uninterrupted traffic movement during the road maintenance work. So an efficient detour plan is essential to reduce the traffic disruptions, but to design an effective detour plan, it is very important to identify beforehand the potential short-term and long-term effects due to the proposed detours on the traffic operations. A literature search on this topic led to the conclusion that there are many researches done on the construction work zone, but very limited studies that examine the impacts of complete road closure and detours on traffic operations. Local studies are recommended to reflect the impacts of local conditions. So therefore, in our study, we considered a recently completed bridge replacement project Now I would like to brief the project. This project was about the reconstruction work of 1.5 mile road segment of I-2059 near downtown Birmingham. The location of the project is very crucial, and it is one of the busiest road segments in the downtown Birmingham. While the current traffic flow is 165,000 vehicles per day, it was designed back in 1970s only for 80,000 vehicles. So, and it is also anticipated that the traffic volume for that segment will exceed 225,000 by 2035. That is why these intersections roadway capacity was needed to be enhanced. And considering the traffic conditions and carrying out the construction works smooth in such a busy road, this segment had to be closed for the entire year 2019. And for offering the alternative routes to the motorists during the road closure, ALDOT along with City of Birmingham and Regional Planning Commission of Greater Birmingham prepared a detour plan. So the purpose of our study actually is to assess the impact of detours on traffic operations at and around the road closure in Birmingham, Alabama region by understanding the changes of motorist travel behavior during the road closure. And that's why we actually followed this methodology to conduct our study. Like first we had to select our study area, then data collection, data processing, and finally producing maps and graphs and statistical. We also conduct a statistical analysis for our study. So this is the study area. It was chosen mainly based on ALDOT detour plan, as well as by analyzing the ArcGIS online roadmaps. Here, the exits of starting and ending points of the road corridors are shown. The study area consists of 9 major road corridors, which were divided into 70 road links. As the roads are bidirectional, that is northeast bound road and southwest bound road, I prepared separate road maps for each road directions. So this is the maps for northeast road bound. So here actually these segments there is actually 35 segments, and these are numbered 1 to 35, and this is the maps for southwest road bound, and these are numbered as 101 to 135. So 35 road segments in each directions. So the data collection, we collected the travel time data from Federal Highway Administration sponsored NPM RDS, that is National Performance Management Research Dataset website. After finalizing the roadmaps, it was synchronized with the NPM RDS dataset. As per NPM RDS dataset, the selected area had actually 411 TMCs, that is traffic message channels. So for northeast directions, there were 205 TMCs, and for the southwest directions, there were 206 TMCs, which actually we actually need to collect 15 minutes averaging travel time data for February 2018, that is before the road closure, February 2019 during road closure, and February 2020 after reopening of the road. From NPM RDS website, we collected 10 data points for weekdays morning peak hours with 15 minutes interval starting from 6:30 a.m. to 9 a.m. and 10 data points with 15 minutes interval for weekdays evening peak hours starting from 4 p.m. to 6:30 p.m. There is 20 time slots data point gathered for each weekday of the month of February 2018, 2019, and 2020. So as we gathered our raw data were travel time. So but we in our analysis we use the travel time index, that is TTI. So thus we had to follow several steps to transform TTI per road segments from monthly 50th percentile travel time per TMC, that is total 400 TMCs to 70 road segments we had to convert it. So as there were some missing value, we consider zero values where there were missing value. So in the TTI maps, road traffic conditions were labeled as little to non-congestions to severe congestions based on TTI value. So green color of TTI value 1.522, which indicates mild congestions. Golden color is used for TTI 2 to 2.5, which indicates moderate congestions. Red color is used for TTI value 2.523, which indicates significant congestions. And dark red color is used for greater than TTI greater than 3, which indicates severe congestions. And TTI value less than 1.5 indicates little to non-congestions. Data analysis and results. We divided our data analysis and results part into 4 segments. In the first segments, TTI maps of road segments were developed using ArcGIS software for February 2018, February 2019, and 2020. Morning peak hours and evening peak hours separately. So then we also prepared some graphs along the study corridors to see the TTI variations in each 20 time slots. That is 10 time slots at morning peak hours and 10 time slots evening peak hours for the whole 3 years. After that, we identified which roads were vulnerable during road closure based on ALDO designated detour plan. Finally, a statistical analysis was done to conduct the statistical analysis. T-test were performed to compare the TTI changes significance from 2018 before closure to 2019 during road closure and February 2018 to February 2020 after road closure. So now we will see the TTI maps. So here actually I am presenting the evening peak hours TTI maps for 2018, 2019, and 2020. This is the TTI maps for February 2018, before before the road closure. So from this TTI scenario, we can see that the except I-65 southbound segments, all the interstate had decent TTI, which indicates little to non-congestions. Apart from the interstate, some segments of US 31, US 280 near I-459 were showing severe congestions. These are very small pictures, like it is really difficult to understand by seeing these pictures, but to reduce the file size, I had to compromise with the quality of the picture. And this is the map for February 2019. That is during road closures. We can, like, at least it is visible that there are more reds and dark reds in this map. So this map is showing that the traffic conditions during February 2019 based on highest TTI value of evening peak hours. It can be observed that unlike the February 2018, several road segments of I-65, I-459 was showing higher TTI and had a mild to severe conditions. Apart from the interstates, the entire US 31, US 31 280, eastbound of US 280 road corridors had severe congestions. Even the TTI of First Avenue North deteriorated from February 2018 even. So I don't know, like actually this, if you can see my cursors, this is the segments that actually closed for this project. So that's why the roads nearby this road are affected much. And for this is the map for February 2020. So this map is showing a similar TTI trends of February 2018. So this map is actually showing the percent change of TTI at evening hours from February 2018 to 2019. So these are the percentage change. So we can see that these the TTI percentage change shows similar trend. It is actually as this is the evening, but this may be the morning peakers may be showing actually the same trend. Here actually 60 out of 70 road segments TTI increased from 2018 to 2019. TTI increased significantly in most of the study road segments along I-65, I-459, I-59, US 31, US 280, and First Avenue North corridors from February 2018 to February 2019 during the evening peak. But the TTI percent change for I-2059, I-20, I-59 road corridors are not significant. So, and this is the percent change of TTI at evening peak hours from February 2018 to 2020. So here we can easily see that from these three segments before and after road closures with some minor exceptions, 3 segments of TTI increased between plus 25% to plus 50%. Other than that, similar like most of the TTI segments decreases from February 2018 to 2020. So these are the actually Aldor prepared detour plan. It is clearly this actually detour plan is for the interstate. The left one is for westbound road closure, and the right one is actually for rightbound road closures detour plan. So it is it is clear. It can be clearly shows that from these detours, the Aldor actually suggested the detours using I-459 southbound and I-65 northbound for eastbound road closure, and detours could be made through I-65 southbound and I-459 northbound. So these are the Aldor provided detour plans for the local roads. From these local detour plans, we can observe that the segments 18, 20, and 118 and 120 of I-65 northbound, I-65 southbound respectively, and segment 30 and 130 of US 31 280 northbound and US 31 280 southbound should be affected due to the road closure. The list of the probable road segments based on Aldor detour plan is furnished in the next slides. So out of the 70 road segments, we sort out that these are the road segments that will be that should have to be affected most due to this detour plan. So as per Aldor designated detour plan, during the road closure, so we can see that the road segments were from I-459, I-65, and US 31 280 should be affected most. Here, from the entrance and exit roads from Birmingham Central Business District, we can observe that for the entrance road segment 118, 120, and I-65 segments 130 of US 31 280 southbound, and segment 18 and 20 of I-65 northbound and I-30 of US 31 280 northbound should be affected. For exit road segments 30 of US 31 280 northbound should be affected. Actually, these the next slides are representative of TTI changes that is documented during the data analysis. Results from 2 corridors I-459 and I-65 PM peak conditions are presented here, and more details are available in the project data draft report. So these are the TTI changes scenario over the 10 points of evening peak hours in each segments along the corridor I-459 for 3 different years. The left side graphs are showing northbound, and the right side graphs are showing southbound segments of I-459 corridor. From the graphs, it is clearly visible that the TTI of 2019 is higher in all cases, and for segment 9, it is near about 2 at 4:30 p.m. and also 5:15 p.m. So these are also some more segments from I-459 corridor. So here we can see the similar trend. Segments 10 and 110 and segment 12, and this corridor had higher TTI value into February 2019. However, in each cases TTI of February 2019 had the higher value for the road corridor of I-459. And these are the TTI changes over PM peak along road corridor I-65. Overall, the northbound of I-65 corridors experienced much higher congestions in 2019 compared to before and after the I-29 construction project. These are the some more maps on corridor I-65. So at the evening peak hours, northbound segments 20 and southbound segments 117 and 120 along the I-65 corridor had low TTI ranging from 1 to 1.5 on average for the entire period to time that was fairly consistent for all 3 years considered in the study. So these are the actually t-tests that were performed to determine if the observed difference were statistically significant or not. So here the comparison between February 2018 and 2019 as well as February 2018 and 2020 on a segment by segment basis. This is the t-test results that compare TTI values between February 2018 and 2019 for evening peak hours. So here we can see that 58 study road segments show statistically significant differences, which in turn confirm that traffic volume increased on those segments as a result of I-2059 road closure. Once again, all segments included in the ALDO Detour plans showed statistically significant change in the TTIs before and during the construction project, which indicates motorist compliance with proposed Detour roads. So here it can be observed that TTI values for 54 out of total 70 segments experienced statistically significant changes at evening peak hours between February 2018 and February 2020 after facility reopening. This hints that some permanent shifts in travel patterns may have been taken place post-construction as motorists may have become accustomed to the alternate routes, thus choosing to keep them even when diversions are no longer needed. So the study analysis showed in conclusions by comparing the TTI value between before and during road closure. In case of I-2015 and I-59, I-20 corridors, the changes were between -15% to 10%, which is not significant enough. But in case of I-65 northbound, TTI increases roughly 40%, and some segment of I-459 TTI increase by 50% to 100%, which are remarkable. But US 31 to 80 and US 31 came out as worst segment due to road closure. As a point, at a point, TTI of segment 30 was reached up to 35, which is so. So hence the study. In contrast, the TTI test results of TTI comparisons, several road segments of I-59, I-2059 corridors were insignificant. Hence, we can say that the study confirms the motorists choose the ALDO provided detour plans as the traffic patterns of those corridors in February 2019 reflected those choices. So the limitations of our study is like we have taken only 1 month for each to compare the traffic operations impacts, it would be great if we could pick some other months. Unfortunately, because of the COVID effect, traffic pattern changed after mid of March 2020. So also traffic data of local roads were not available in the NPM RDS website. Only major roads traffic conditions were analyzed in this study. There was some incidental closures for 2 to 3 days in the local roads around the closure, which could not be assessed in this study. So the future in to get motorist opinion regarding ALDO designated detour plan as survey work would allow us to know the actual feedback from the user in realizing ALDO detour plans effectiveness. In fact, a survey of road users is currently underway to assess how the motorists choose their detour road during the road closures. So this study will actually help in quantifying the impacts of travel patterns changes in response to the I-2059 bridge reconstruction projects and provide insights about the likely influence of detour planning on traffic operations in and around the affected areas. The lesson from the study will provide valuable guidance to the agencies responsible for planning, design and operations large-scale construction work, and will assist them in executing successful traffic management plans in future. So finally, I want to acknowledge the supports from the STRIDE, ALDOT, as well as also the Regional Planning Commission of Greater Birmingham for providing the access to the NPM RDS dataset and technical support. So thank you for your attention.
And thank you, Saiful. I don't see any questions, but I encourage anyone, if you have any questions for Saiful, please put them into the Q&A pod. I do have one question for you, and I'm curious to know why you settled on TTI as your measure of choice as you went through this study.
Well, actually, so by TTI, we can have the real pictures of the roads, as there might have lane changes, and number of lane could be changed there, different number of lanes. So we can't actually, if we take the volume, so we can't actually represent the real scenario. And also by the time we could, time is also dependent on the length of the road, so that's why we use the TTI.
Okay, well, thank you. I don't see any, oh, actually I got one question that just came in. Were there any other incidents along those segments that were recorded and considered for analysis that would overlap with the detour and increase the TTI further?
Well, actually, that's a great question, but in our study, we try to sort out, is there any other construction work is going on around our project area, but so far in actually during the 2019 road construction, there were not that much construction work around the apart from this project, but from record, there were actually road construction going on. That is from not this area, that is that belongs to another area. There were construction works that were going on 2018. So that's why some road segments were showing a greater TTI in 2018. So yeah, we actually didn't consider any other projects impact in our study.
Okay.
Yeah.
Well, thank you, Saiful. That is the end of our time there. So we are going to move on to the next presentation, but definitely thank you for your time.
Thank you. Thank you.
Our next presentation, we have a trio of presenters, all from Kimley-Horn. So this presentation is estimating benefits as a method for analyzing projects for decision-making and deployment of transportation systems management and operations. So our three presenters, first we have Kenneth Smith. Kenneth is a project engineer with experience in ITS design and planning. He is also a technical expert for transportation technologies, such as curb management and parking technology. Kenneth graduated from NC State University, and in his recent work has served clients including US DOT, state DOTs, MPOs, and airports. Second, we have Natalie Smuz-Mengelkoch. Natalie has 20 years of diverse experience within ITS and TISMO planning and engineering, and has led projects within all implementation phases from programming, planning, and systems engineering to design, integration, and operations. And lastly, we have Inger VanOsdell. Inger graduated from NC State University and has 20 years of experience with ITS planning and design. She mainly works on projects with state DOTs, but also with the US DOT and MPOs, and was able to work on a project in South Africa for several years. So for that, I am jealous. And she is currently leading the upgrade of the Gastonia signal system for NCDOT, which was also the first signal system that she designed in 2005. And you guys can take it away.
I can start. Kenneth, can you maximize that? I think he has it. So hello, good afternoon. My name's Inger VanOsdell, and I'll be the first one presenting and starting us off with looking at estimating benefits as a method for analyzing transportation systems management and operations, or otherwise known as TISMO projects. TISMO and ITS projects provide real-world benefits to their end users, but sometimes it can be difficult to quantify these benefits, such as not sitting at the congestion at a traffic signal or lives saved due to the implementation of curb speed warning. Deployed TISMO projects have demonstrated the ability to improve safety, enhance mobility, and reduce emissions and fuel use. Yet for many decision makers, there continues to be a tendency to address transportation problems by adding lanes or building interchanges and roads. I'm not saying that these solutions are bad, but we want to provide a way to present decision makers with other ways of thinking of the benefits, specifically with TISMO projects. The next slide focuses on the business case. What is the benefit cost ratio or return on investments on different type projects? TISMO projects have the potential to provide fruitful benefit cost ratios via implementation of different strategies. TISMO investments offer DOTs the opportunity to realize a better return on investment than traditional roadway projects. For example, a traditional roadway project could see, as you see on the at the top, a BCR of 2.7, which would mean that for every dollar spent, that there was $2.70 of benefits. But you can also see that there are some TISMO strategies, such as coordinating traffic signals or providing real-time traffic information that will have a much higher return on their investment. And the light blue is the slight sort of scale of the high end of the BCR, where the darker blue is the lower end of the BCR. And then the next one is, then we get into, okay, what is this methodology? Well, FHWA created a tool for operating benefit cost analysis. It's also known as TOPS-BC, and it's similar in ideas, and it has typical traditional TISMO benefits, but what we'll be presenting is more customizable and also can be used for non-traditional TISMO strategies, where we've done fog warning systems, safety service patrol, Q warning, a lot of different strategies we've been able to look at providing a benefit or BCR for these. And what is our primary tool for doing this? Is the research and data. The internet and Google are your best friends here of just trying to familiarize yourself with the research that's out there for the specific strategy you're looking at. And then we do this like on the next slide. We can look at, we've created sort of the 6-step process to do this. We start with what I was just saying, identify the resources. ITS deployment evaluation database has a lot of, it has a benefits database and it has a cost database, which has plethora of information to find about a specific strategy, great systems to be able to search. And then you can also TRB and other published evaluations. And then you can look at site specific, where you're going to look at crash data, RIDIS data, other data that could be provided by a local agency. So first you have your identify your resources, then you go to estimating your benefits, where you're going to look at, you have safety, mobility, energy and environment, efficiency, productivity, and customer satisfaction. The first 3 are much easier to find a benefit for. Say if you implement Q warning, what is the safety benefit of that? What would you see of reduction of crashes? So once you estimate your benefits, then you'll go to step 3, monetizing your benefits, where it will be the same system. So if you have reduced your crashes expectedly by a certain amount, what is the amount associated, say, with the safety benefit of reduced crashes for PDO or fatalities or injury crashes? And then that would be moving on to step 4, where you would estimate your cost. So you have your benefit, and then it's going to be compared to what the cost is. So what is the capital cost? What is it going to cost to design and build that specific TSMO strategy? And then along with that, we don't want to, the operations and maintenance can end up being a big amount of money that we don't realize sometimes. So what is the total cost of this TSMO strategy? And then from there, you're able to, you have your benefits and then you have your costs. You're able to conduct your benefit cost analysis. And it can be in the form of the benefit cost ratio that you saw on the previous slide, or a return on investment that's presented in a percentage. And once you have that information, you will go to, then you want to communicate your results, and you can communicate it to different people, the people that have the money to decide what to do, a certain amount of money, how do you solve problems, or operators, or to the public. Kenneth and Natalie are going to go further in depth of each of these different steps. So Kenneth can go ahead now.
Yep. So let's go through some examples on how to apply all this methodology. We're going to start with one strategy that is widely used and has a lot of research for, like CCTV cameras. In this example, we're able to identify different resources on the benefit for cameras. But in order to find the right resources, it's really important to really determine the main use for the camera. We're talking about the area. Is it urban? Is it rural? You're probably not going to get the same benefit if you are in the middle of Manhattan that if you are somewhere else in a rural setting. You also need to think if you have an area that has currently no coverage, or is it an area with partial coverage right now? All these questions are going to allow us to find articles and research that can be similar. Main point here is that no 2 implementations are the same. So the idea when working on ROI is to find systems that are as similar as possible to get a good representative source. So we're talking about the steps before. So the first step here for the cameras, identifying resources, is the foundation and conduct the benefit cost analysis. It includes identifying trusted and verified resources that will serve as the basis for the analysis. As you can see, for the purpose of this example, we're proposing CCTV cameras for freeway incident management and found a couple of different resources on safety and mobility. For safety, it has been identified that cameras reduce secondary crashes by 40%, and then they can also reduce delay by 5%. So let's walk through one of those just to see how we can monetize and estimate the benefits. As mentioned before, we're assuming a reduction of secondary crashes by 40%. So in order to calculate the benefits for an agency, we first need to determine the amount of secondary crashes. Sometimes you can get this data from different agencies. Sometimes, like in this case, we actually need to dig a little bit further and do some research on the amount of secondary crashes. Doing this research, we found that around 20% of crashes are secondary. So we can get now data from the agencies on crashes like PDO crashes, people and injury crashes, or fatalities. With that way and with the numbers that we found for the average cost for each of those, we can monetize the benefits just by trying to figure out how many crashes are going to be saved. So after getting the benefit data for the safety, we're also be able to apply mobility and energy and environment benefits after the research that we did. So for mobility, using REDIS data, we can get the number of incident delay and also apply a passenger vehicle truck ratio for the road to monetize the benefit for every minute of delay saved. For energy and environment, we can also estimate the delay savings and calculate CO2 emissions that will be saved. So as you can see, there are a lot of different ways that you can get the benefits. It really depends, part of it, on the data that you can find and some of the benefits that you can get. So you can see on the left side of the screen that we can get data for safety, mobility, energy and environment, efficiency, productivity, customer satisfaction. So try to use the data that matches more the strategy that you're applying. Then we jump into step 4 and 5. So step 4 would be to estimate the cost over a period of time. And like Inger was saying before, users need to not only identify capital costs, but also operations and maintenance costs estimated for the system components. When estimating costs, it's really important to ensure that all the capital costs are included. You need to identify all the components for this application that make up the entire system. So in this case, for the cameras, you don't only need to think about the cameras, but also talking about poles, cabinet, foundation, power, comm, integration to the advanced traffic management system, pretty much everything that encompasses adding the cameras in the place that you want to deploy them. So for step 5, then we talk about conducting the benefit cost analysis. So estimating monetized applicable benefits for safety, mobility, energy, environmental efficiency, productivity, and customer satisfaction. You need to also think about extrapolating that cost over a certain time period. For the sake of this example, we use 10 years, but it's going to really depend on the project you're working on. Likewise, you also need to think about extending those costs for capital, for operations, maintenance costs, just to think about matching apples to apples. Assumptions might need to be made as well about replacement costs for the equipment over the time horizon. Also think about inflation and other factors. But at least for this, just for the sake of this example, we're not assuming any replacement. We think the cameras can last 10 years. There might be some escalation costs for maintenance, but it just depends on who's your audience and what numbers you want to get. But at the end, just as an example, we get a PCR here for 10 years, around almost 14 to 1, an ROI of around 1,200%. This is also something to consider, that you need to think about the audience that's going to be receiving these numbers. Some people like the PCR, some people like the ROI number. Just think about your audience and what you want to tell them. So as a second example, let's just quickly walk through another example with something a little bit newer, like variable speed limits. So for variable speed limits, there are different ways to apply it. You can think that sometimes you've seen it on a gantry with DMS signs, to cutout signs, like shown in the pictures. Given that it's a technology that is not as widely available right now in a lot of places, there are probably a few resources online, just fewer resources compared to the cameras. But you can still find some data as shown here. You can see the average reduction in number of crashes is 8%, and average reduction in travel time is around 5%. So going through the example here, the main takeaway, because you can see similar things, we're able to find mobility numbers, safety numbers. For energy and environment, don't think only on like CO2. You can also find data for other greenhouse gases that you can put in there. Main thing here is that we want to show how even on this side, the variable speed limits are going to have a higher benefit after getting all the calculations for this specific side compared to the cameras. Benefits are going to be way higher, but also think about the cost, O&M, like we were mentioning before. At the end, all these numbers are going to change. There's no just one number that's going to apply to variable speed limits, not just one number for CCTV cameras. Things are going to change depending on the data that you have, where you're placing them. So just something to consider. So Now I'll give it to Natalie so she can talk a little bit more about step 6 and how to communicate this information.
Thanks, Kenneth. So Inger and Kenneth have talked about how to calculate the benefits and compare it to the cost. Now let's talk about how to communicate the results. And so I think this is a really critical piece that sometimes maybe doesn't get the thought that it deserves. And it seems straightforward, but I think sometimes we're just moving and don't think about it as much as we should. So considering who your audience is and what you want to communicate with them, I think is really important. And so thinking about what is relevant and what is relatable to them, particularly within different audience groups. And we're going to talk about decision makers, operators, and the public. Next slide, please. Thanks. So decision makers. And so these are the people that are responsible for prioritizing projects a lot of times. They're required to demonstrate fiscal responsibility. And what we found in our experience is that communicating BCR, so the benefit cost ratio and the ROI to these groups has been really successful. And so, you know, and depending upon your particular group, they may require it to be in a certain format and such. And so, and depending upon how you're using it to compare. So for example, we've worked with clients who have used benefit costs to be able to compare a TSMO strategy or ITS deployment alongside, you know, to a traditional roadway project or even bike ped project. And so this has been a good way to communicate this and leverage the information and the data to be able to demonstrate the value of the TSMO projects. And so you can see the example here on the left, and I know it's small, it's just meant to be a really more of a prompt for me, but essentially on the left, we've used it to compare specific TSMO strategies along, you know, a particular, you know, within a particular area. And so determining it, you know, determining what strategy might be effective for a specific case. Whereas on the right, what we've done is we've looked at a set of strategies and, you know, considered deploying them within a certain zone or a certain area and looked at what the return on investment or BCR would be within the particular zone. And so that's just two different ways that we've, you know, supported clients using this methodology. Next slide, please. And so then thinking about operators and how operators might leverage this information. So operators tend to be the people that are developing the projects, and they're the ones that are typically depending on the KPIs, key performance metrics or indicators, as well as various metrics and so forth. And so we found that BCA can help support this group within their project development phase. So on the left there, essentially what we've done in the past is help clients to develop tools that support efficient benefit cost analysis for a particular project. And so they've used it in project vetting. And so just thinking about, am I going to get, you know, more bang for my buck if I consider a camera in this location or that location and so forth. Or in the case where maybe a particular organization is considering less traditional type of deployments, you know, wanting to think through how that might be, you know, the benefits estimated for that and how they can use that to determine if this project is viable. I would caution that you know, something I think we probably might not have mentioned before is we tend to encourage people to consider this as one tool in the toolbox of development and so forth. It's not necessarily the end all. And there's, of course, different scenarios where the numbers may not reflect what is out in the field in a meaningful way, or there just may be some nuances, specifically in the non-traditional deployments. They can be a challenge to represent, what we know in our heads, represent with the numbers if the research isn't there to support it, just because it's a newer deployment type or something like that. But, and then also, a lot of times we've helped support, clients in with particular projects and operators that are looking to seek funding for a particular project. And so BCA can be used to support that effort as well. And so this may not be a demonstration of what the monetized value of the benefits are, but rather the actual numbers themselves. So you see an example there of something we provided for a CMAQ application, where we've used the same approach, the same methodology, and used that, I think it's step 2, where we've estimated the benefits. The same can be done for like the number of crashes and congestion reductions as well. So next slide, please. And so finally, we'll talk about communicating the results with the public. And this is an area, I think, as an industry, we have a lot of opportunity for growth. I know in my experience, I have not seen a lot of communication with the public, specifically about the benefits of transportation technology and how, how valuable these investments are. Certainly the sort of, I think we do a good job of communicating some of the more exciting ones, but the day-to-day value, and it's hard, like as Inger said, it's hard to represent this and make it tangible and relatable to specifically to maybe a less technical crowd. However, what we have done in the past, and here are kind of 2 examples of that, is try to make it relatable to the public. So how many additional hours each year are available to spend with family and friends? How many gallons of gas are not required to be purchased, and fewer emissions? So these are just a couple of examples of that. And so, like I said, I feel like this is an opportunity for growth for all of us. And I apologize if you're doing a great job of this. I just haven't seen it yet. And please feel free to share and provide feedback to us either here or after the fact as well. And I do want to just touch on one more thing. Kenneth, if you can go to the next slide. So talking about communicating the results, and then if you sort of step back and think about how benefit cost analysis can be used from a more holistic nature, it can be part of the project lifecycle, and really as a programmatic process, really. And I think that lends itself nicely to be able to make data-driven decisions throughout the life of a project, throughout the life of your, program processes, really. And so I'm just going to step through this quickly. The project development phase, we sort of talked about that, the opportunity to leverage BCA analysis to vet projects and determine if, one makes sense versus the other, or vice versa, and then and using it in that manner. And then stepping into the planning phase, using it as a way to help support prioritization, specifically with mainstreaming TISMO projects. Understanding that can be a challenge sometimes. I think BCA really can help support in that effort. And then, moving into design and deployment, thinking about how the data and the metrics that are going to be used to help support within, your operations and optimizing your system, those key metrics can be used such that they can be integrated further within your BCA. So, for example, if you have, detection or something that you're going to use and maintain a database or something like that, then those key performance indicators can be used to then enhance your BCA analysis for the particular strategy type. and then within operate, measure, and evaluate. So I know as an industry, I feel like we did a great job of this, you know, in the early aughts and so forth, when we were all encouraged to do all of the evaluations of ITS projects as part of federal funding. I know some of that I think has waned a little bit, but that evaluation piece of it has been critical in encouraging and being able to demonstrate the value of these types of strategies. And so wanting to continue to evaluate and have a strong program of evaluating and, you know, being able to share that information with others, I think is really key. And leveraging the data that's used within BCA and then likewise throughout the whole process, I think is a great way to do that. And to, you know, to the point of the next one here, sharing the results. So sharing that with the industry, you know, widely, I think has been something that we obviously have leveraged through the ITS deployment evaluation databases. And so that's a great resource if y'all aren't using that right now. You know, bookmark it immediately. And in fact, I'll put it in the chat for everybody as well. But this is a great opportunity to see what others are finding within their deployments, and can be a great resource to use, and then also to share your evaluations. And I know, you know, we find research and evaluations from all across the country there. So it is really handy. And then that last piece showing the kind of feedback loop. So you've done your evaluation of a particular strategy. And so what this can do is help enhance and gain accuracy in your BCA for the next deployment of this type that you want to think about. And so, you know, if you just think about it, you know, if you're, you know, focused on the key metrics that can be leveraged not only for the operations and management of your system, but also for the demonstration of the value of your system, that is a great opportunity there. So thank you for your attention, and we are happy to take any questions at this time.
Thank you to all three. We'll pause here just for a minute, just to see if anyone does have any questions in the Q&A pod. I guess I'll pass on one question again. You know, for these new strategies that are up and coming and are newer, how easily are you able to identify benefits that are tied to those, you know, up and coming strategies that haven't been deployed too many times in the past?
Natalie, go ahead.
Indeed, it is a challenge. And so, and we have done some squirrely ones, that is for sure. So what we've typically done is try to step back and think about the intent of what that strategy is. And if there isn't available research to support the specific benefit, like if it's a pilot project, for example, what we'll typically do is consider the intent and then lean on research that is as close as possible. And so again, back to the sort of, you know, cautionary points that I put out there, that's an example of where I wouldn't encourage somebody to use this as the end all, nor do I think that it should be, you know, ever necessarily, but you know, you do have to, what we say sometimes is you kind of have to squint a little bit. This is sort of in between a science and an art. And so having that experience to sort of be able to feel what makes sense, I think is key.
Great, thank you. Yeah, thank you again. We're going to turn it over to Dale for our next presentation, but we do appreciate time from all three of you. Our next presentation is going to be from Dale Bartlett from Wavetronix. It will be providing data points to understand the spatial relation of vehicles to the situational awareness of an intersection. Dale is an industry research manager for Wavetronix. He lives to discover the latest and future trends in the industry designed to help provide the latest in innovation and technology to the end user. As an industry veteran of nearly 28 years, he has seen the industry emerge from the traditional loop to a variety of detection technologies that have revolutionized the industry and vehicle data collection. He has worked on many notable ITS and intersection projects in the US, China, and Australia, and has seen the benefits that accurate, reliable data can do to make the world roadways smarter, safer, and more efficient. So with that, Dale, and I know Dale's presentation is a little different, so I'm going to spotlight him for everyone here. So he'll show up full screen, but Dale, take it away.
Excellent. Well, thank you. Yeah, this will be a little bit different. I wanted to give a little bit more of a presentation style to it, and hopefully it will all work out to everyone's benefit. I'm honored to be here today. I've loved the past presentations. I think some of them will tie in a little bit to, especially the last one, into what we're trying to show in regards to technology. Over the 25 years in this industry that I've spent, I've seen a lot of change. Mostly the last few years, it was extremely slow in regards to technology in those first parts of my career in this industry. But I love to understand this amazing market and look for the holes that need to be filled with specific technology that can solve very specific problems that you may be facing. There's been a lot of talk over the years in regards to radar and its ability and being able to get detection out of the ground and being able to do a little bit more with it. What I really want to do in this presentation is show you technology that is available now that takes it and completely changes maybe the way that you look at an intersection, especially that situational awareness of your intersection. What's happening? What's the situation? What's going on there, as well as the spatial relationship of all the objects as they're moving towards this intersection, and how do we mitigate some of those issues? So so what are the different situations at an intersection? How do we best manage these situations based on data points gathered in the roadway? And finally, what are the technologies available today that we can fully understand that spatial relationship of different objects to the roadway to provide the data points that mitigate the known and maybe even unknown situations that might occur? One of the things that we may want to look at is how others in the industry have tried to solve this or are solving this this problem in the industry. And one way is through a software approach, using open source softwares, feeding it with a bunch of data points. But are these the right data points? Are they limited sometimes to manufacturers' capabilities of being able to provide you with what you really need for that upper part of the traffic signal operational pyramid that is so vital? And maybe we'll go just a little bit into that. Everyone wants to get up to the system control aspect of their intersections, of their system overall. But we need to tackle some problems that occur before we do that. One of them, and probably one of the most important things to do, is get good intersection local control. That means, do you have trust in your timing plans? Is the equipment that you're utilizing detecting properly, preempting properly? Is the traffic flowing well? But even to get to this level, there's really two bigger hurdles that we have to accomplish in the triangle. Agencies are dealing with work order after work order, trying to solve the problems that sometimes their detection or lack of understanding how that is supposed to be implemented in the roadway works. And in order to utilize high quality data with less maintenance, it really is demanding, utilizing demanding hardware is really the key to that. And that really becomes the foundational part of the whole pyramid that we're looking at here. It's the foundational aspect of the traffic signal operations pyramid, and that is the installation and communication capabilities of the detection that's used out there, as well as how do you communicate to monitor those intersections. Some agencies have done this and gone corridor by corridor and with this pyramid and utilizing things like adaptive systems and that to improve a corridor at a time. Other agencies have gone intersection by intersection, first improving the detection and then the communication, then moving on from there. So there's different ways that are being utilized to tackle this, but ultimately it comes down to making sure that the detection and communication is as maintenance free as you can possibly get it to give you the best local control, because that data is going to feed your system data. So the ultimate, what you ultimately want is that system control of your local intersections. So what of other industries? If we looked at what can we maybe borrow from other agencies that utilize some of the similar technology to be able to do this? Well, air traffic controllers have developed the ability to see the full coverage of both their spatial awareness and the situational awareness of all the traffic that's in the skies. They have information about what each vehicle is, or airplane in this case, each object is, what type it is, its location, its speed. There's a lot of data that goes into this so that they can have the right trigger points and the right data sets to be able to take care of the situations before they happen. So as these approach, where are they in relationship to one another, both maybe in this case, elevation-wise, speed-wise, direction-wise, all of that type of thing. Early on, a lot of this was very manual, and so it was more in that intersection control they were trying to control this more at a human level. And then as technology improved, they were able to get more data points. Then they were able to move into the system control that they desired. Are there lessons there that we can learn from this type of approach to make intersections safer and smarter and more efficient? Well, let's look at some of that capability, and let's see how this similar technology is able to work in controlling intersection situations. Let's look at some of the different situations that use traffic engineers and professionals need to be aware of. And some of these, it's not like you need to be aware of them, you're aware of these every day. One situation that you may seem obvious is phasing. Phasing may not seem to be a situation, just something that merely happens, but each one of us knows that there's a lot that goes into the termination of one phase and the start of another phase. Some of those situations can be better mitigated if you're aware of maybe the approach speed of the vehicles in relationship to the stop bar and where it sits within both the speed and the positioning of that vehicle. A lot of people consider this being the dilemma zone, decision zone, and being able to make those decisions. But in reality, what it is, it's the dynamic spatial relationship of that vehicle in relationship to the situation that's going to happen at the intersection timing, with the intersection timing. So is that intersection timing changing, and where are those the spatial relationships of those objects as they approach? Another situation can be split failures. Now that's not enough green time and can be caused sometimes by inadequate controller timing, but most of it can be also traced back to poor detection and inadequately performing. Can you trust the detection being used? It goes into that maintenance aspect of it. Is it giving you the right data points? I'm sure some of the questions that you ask all the time, is that really what I need to know? The other thing that might be something in regards to spatial relationship is to the spatial relationship of vehicles to another vehicle. we a lot of times call this gap between the vehicles, but understanding the termination of your intersection is vital to those gaps, to find those safe gaps. If you've got traffic waiting on a side street, to be able to safely transition that intersection, and finding more gaps is even more important. So not only knowing the time period of maybe 3 seconds between vehicles, but understanding the relationship of speed as it goes in regards to that, and the dynamic speed of vehicles speeding up, slowing down in relationship to one another, provides you with more information to find those gaps. And that's the true, again, what we call true spatial relationship of those vehicles. So if we look at an intersection, we can see certain areas where data either it can be gathered or is typically gathered, especially up near the stop bar, the limit line, those types of areas. What else do we know about this intersection? What could we expand our view on and see more of? But even more so, can we provide ongoing data sets that is vital to the operation and situations that will occur at this intersection? So let's take a look at this. What we know maybe is the speed of this approach. We know the speed of the side street. We know that we have vehicles stopped here. What's the information that we can gather from all of that information there? We have a situation where right now, this is the green phase, but we have no vehicles here. What information can that tell us in regards to this? We have other information such as vehicles approaching the intersection on red. How many vehicles approach on red? How many vehicles approach on green? What are the types of data sets that we can gather from that? We have vehicles that are needing to turn. We know that this is a double left, it's a protected, those are other things that we can know about this. We have a vehicle turning. We have a vehicle approaching on green. What other information do we need to know about that vehicle as it's approaching? And maybe we've got throw in some bicycles into this mix, and then we've got maybe a large vehicle approaching. What data do we need from this vehicle? Those are the types of things that we need to know. And how do we gather that information as we look at this? So if we look at it kind of like air traffic control, could we see not only the distance between vehicles, maybe it's the distance between vehicles as they're approaching infrastructure such as stop bar, and then do we understand the type of vehicle that's approaching? What if you were to no longer had to add additional, as vehicles were trying to get through and have that passage time? What if you were no longer to have to worry about adding additional passage time that makes intersections inefficient, and you could utilize dynamic tracking of vehicles all the way in? What would that do to make an intersection more efficient? Well, let's look at the different ideas. What we really need to do is that local control of that intersection and being able to provide those data sets for that local control. Then we can pass that information on to get to the systems that rely on that good local intersection control data. Without first securing the good data points that is needed by the engineers, and a lot of times it's not what a lot of manufacturers even, that we want to be able to create, format the data to just make it look pretty and have really pretty data sheets and formats and those types of things without understanding the reliability and accuracy of that data. If you are going to build that strong pyramid, you need the right data and it has to be good. It just doesn't have to look good on paper. And that's vitally important when you're looking at these different systems. So I'm going to switch views here really quick on you. This kind of creates the uniqueness of this. And we're going to look at it. We're going to kind of whiteboard this out a little bit if you will indulge me a little bit. If we have traditional type of detection, whether it's loops, whether it's zones, whether it's certain technologies of radar that only give you point information, we only see certain aspects of what's going on our roadway. there's so much of our roadway, and believe me, this is not to scale, but there's so much of our roadway that we have no idea what's going on. And can we get that information? And is the information important? Do we know the information of the spatial relationship between these two vehicles, not only as to the type of vehicle, the speed of vehicle? So maybe we need to know the type. Maybe we need to know the speed. We need to know the positioning, and we need to know the positioning and where it is in regards to taking that speed and that position and giving maybe an ETA for critical infrastructure such as the stop bar. Same with these vehicles. All of these vehicles can have it. Where is this vehicle in relationship to this vehicle? How much gap do we have between this vehicle and this vehicle? Not only based on time, but what is it in regards to speed? What is it in regards to type again? What is in regards to positioning? This vehicle is maybe going maybe 55 miles an hour, and this vehicle is going 40 miles an hour. What does that do with our actual gap here? And we only have certain points in which we can gather that information typically. What if we had the entirety of this entire thing to be able to look at dynamically every vehicle's position as it's traveling to there, and we don't have to worry about it? Some technologies within radar give you the ability to put some caveats, speed possibilities to it. But really what you're still looking at is just point data at a particular point further back. What happens as that vehicle has a driveway here and they're slowing down? And yes, they were going fast up until this point, but now they're slowing down to get into the driveway. All of that's critical data to make that intersection run smoothly and to truly understand where is our time to transition that intersection from green to yellow to red when we have this. What if we didn't have to have particular types of detection capabilities to figure out a speed and distance to give you the passage, but we're actually tracking it all the way to the stop bar so we can reduce our passage time to half a second to a second, and again, make that intersection much more efficient as they go through that intersection. What if when, well, we'll get into that a little bit later. So there's some other scenarios there that we can utilize in regards to understanding the, sorry about that, understanding the spatial relationship, and understanding the type of vehicle is something a little bit newer that is available to the technology that's available now. I'm going to show you this quick little video here that's going to show you what happens when a transition happens. A vehicle can stop, but a type of vehicle that can't stop is right behind it. And so we have a vehicle running a red light. We have luckily no one in that right turn lane as they have to make that quick decision to swerve around and run that red light because they didn't have enough information. If we knew what type of vehicle that was, and we're going to show you now what that looks like in regards to the technology that's available to us today, and being able to understand what we can do differently, because those larger vehicles have a stopping distance of between 2.5 and 7.5 seconds in the dilemma zone. And so their stopping distance much larger, so they need a larger dilemma zone. And how does that relate to the other vehicles? As we get these vehicles approaching, we can gather their speed information, their ETA, their other data that they have. But what we really want to also do is gather as this other vehicle comes down in and is tracked here, we now have a different type of vehicle. How do we treat that different type of vehicle differently? What kind of parameters can we give it in relationship to distance, in relationship to speed? And as that vehicle is tracked in, we will find a time when that vehicle at 7.2 seconds is now eligible for making sure that they have the passage going through that. That can be set up, and you have the ability to not only create caveats and other things to make that intersection run more smoothly, but now you have the data sets and the spatial awareness and the type of vehicle, all of those things that you need in order to make that happen. So there we go. What about, utilizing other data sets to understand infrastructure, such as vehicles approach or backing up on a roadway and blocking a fire station? Or what if we had vehicles having to worry about blocking a railroad track, other critical infrastructures? If we look at how that is utilized within here, if we've got say erase some of this information here, if we've got a critical infrastructure such as a fire station here, and we've got vehicles backing up on it, what is the spatial relationship of these vehicles, their speed, their position in regards to this, so that when we see speeds dropped, let's say down at the 3 to 4 miles per hour range, we know we're starting to get a queue up. And can we then send a signal and be able to do that? Same thing with railroad tracks as they're going maybe in a really bad spot to put railroad tracks, but sometimes that happens. Other infrastructure such as a ramp off into the onto the freeway system, and it's really short, and you get cars that back up onto your roadways. Yes, this is an issue that maybe the DOT has to work with, but it also affects an agency in regards to what they need to understand there. So how do we understand, again, where those start happening, not just in certain points, but we have constant data communication with every vehicle. Because what's going on with all of this is the ability to understand the right type of technology that is required. It's not just something that you can just throw together. In order to make those critical points to safety and efficiency, they require technology that is designed for the traffic industry. Just like the radar was designed for the airline, seeing the skies and understanding all of that, we need industry radar that is designed specifically for the traffic industry to solve the traffic problems. Radar needs to be designed and manufactured to give the types of results you as engineers are looking for. And not just something that's just pulled off the shelf type of radar or repurposed from some other industry into it. There's a real difference between building to application and solutions than building to price and just trying to get something out of the ground and do pretty close to what we've been doing before. We need it differently. We need to do that in order to get the system control. So it has to be designed properly. So what we're really trying to do is we're trying to start unblurring the traffic world. And it's kind of ironic that we're utilizing technology other than vision to unblur what we're seeing, because radar has the ability to see just as clear at the stop bar as it does 600, 900 feet back as we track all of those views. There is nothing different in the way that it sees those. There's no pixelization, no narrowing, nothing else that happens in regards to that. So this is vital, and this is something that was just talked about in the last discussion, was that this is vital to the safety and trust of the public. If you create roadways that they can see the improvement on, they're more willing to fund better technology into those projects, but they have to feel like it works. And so when you've got agencies that are proactive and they put that information out to the public and let public know, hey, like, we're trying to give you as much green as we possibly can and get you to your destination, then that makes a big difference. It will give you better data, more data. It will be able to then have the ability to allow you to analyze that data, and that really good data, not just data that comes in a pretty sheet, but data that you can really stick into your system and get the results that you want out of it. The idea is really to see what's possible today, because the data that we're going to need tomorrow and what we're going to have available to it tomorrow is huge. I mean, that's where the big data is going to come from. And we're getting down there. That is coming. Big data is coming down the road. But what we really have to understand, if we're going to understand vehicle to vehicle data, and we're going to understand all of that complexity that comes from, we have to understand where this current smaller data sets are available to us because they're easy to obtain now, and they fit into our existing databases, where big data is more difficult to obtain, and it needs huge databases, and you have to parse that out. If we can get better at obtaining the small data and utilizing it, when that big data comes, we'll be able to utilize it, and that will give us the success that we need. It will lead to smarter, safer, and more efficient intersections. It will help fill the holes in the missing pieces that we have. And more importantly, it'll provide a solid foundation for managing the roads and the intersections that all drivers will have to travel for the next 20 years. And as that bigger data comes, as a vehicle to vehicle and the vehicle to infrastructure and the infrastructure to infrastructure data starts coming, we've learned right now how to deal with those kinds of data sets to be able to make our intersections more affordable. So with that, I just wanted to say thank you. This is our traffic lab. We brought in thousands of people into this traffic lab, and if my email's here, if you want to have a further discussion on this or other types of technology that's available to solve some of your problems, just give me an email and we'll send that over to you.
Great. Well, thank you so much, Dale. I've had one question come in so far. How often is information updated to the controller on a dilemma zone approach?
It is updated on a continuous basis, on a second by second basis. The scanning that is done is real-time scanning, and it is by vehicle per second type of data as that vehicle approaches the intersection. The technology is available to do that now.
Thank you. And I'll leave this here for another minute in case anyone does have another question, but in case anyone's typing out questions, I'll just do a plug for the next session, which the traffic bowl prelims do start at 3:30. So for any of you that are new to Southern District meetings, highly recommend that you attend that and cheer on the students from your section. It is a lot of fun, and we'll get to see which schools advance to the finals. And I am not seeing any other questions come in. So I will say thank you to Dale for your presentation, and another thanks to all presenters. Very informative stuff. And another special thanks to AirSage, who did sponsor this session. And with that, I hope we see you all at the Traffic Bowl prelims, and thanks so much for joining the session.